You can go ahead.
Good morning, everybody. Thank you for attending the colloquium of March 2025. It's with great pleasure that I would like to introduce you Professor Garrison from the Purdue University. I have here a short biography of his academic and research life, but what I want you to know is that he's been one of the first people to work on GNSS reflectometry, and the creator of the, I think it's called here, it's not here, okay. The reflectometry using other sources of opportunity. Maybe you know that this is one of the main topics that we work in our group. So it's for us a really great pleasure to have him here with us this week. He's been for the entire week. Now, the official biography. He's professor in the School of Aeronautics and Astronautics at Purdue University, and he's also teaching in the School of Electrical and Computer Engineering and the Ecological Science and Engineering Interdisciplinary Graduate Program. He was elected a University Faculty Scholar in 2022, and his research interests include Earth remote sensing used on global navigation satellite systems and signals of opportunity. He's the principal investigator of a NASA mission called SoOp that aims to demonstrate remote sensing using P-band signals of opportunity. Before his academic position, he was with the National Aeronautics and Space Administration, NASA, at Langley first and at Goddard later. He has a PhD from the University of Colorado Boulder in '97. He also holds a BS from RPI, because I don't remember how to pronounce this name, and an MS from Stanford University. He's a fellow of the ICE-CSIC and the Institute of Navigation Societies. And from 2018 to 2022, he was the editor-in-chief of the ICE-CSIC Geoscience and Remote Sensing. So, Jim, thank you for being here with us. You have something like 45 minutes for the lecture. You can use that block as reference, but if you want, I can also give you some warnings.
Okay.
The time.
5 minutes, give me 5 minutes.
Yeah, I think we have a bit of flexibility. Okay. Thank you.
Hey, gracias, Estelle. As I said, my name is Jim Garrison. I'm going to talk about my work broadly in signals of opportunity remote sensing, which includes as a subset the GNSS reflectometry. But I'm trying to present this kind of a broader field now, even though it began with GNSS GNSSR. I'm also, I didn't add it to my biography, but this talk is basically what I give for my IEEE Distinguished Lecturer talk. So I've given this a few other places. I'm invited to give it to a few other places coming up. But it's kind of a general overview. I might skip forward some places and spend more time on others than I usually do. But let's start with his broad background. I don't know what everyone's background in this group is. My understanding is the center is largely space science and astrophysics, with Earth observation is a kind of smaller part. So I'm going to give a review of microwave remote sensing and a history of SoOp starting, long before I got into this. That there is a background before me, and specifically what led to GNSS reflectometry, why global navigation satellite systems, which are designed for navigation, were particularly useful for remote sensing, and then spreading into some of the other applications that we're looking at in terms of frequencies, both lower than what GNSS uses, which is L-band, and much higher, and some of the new things we're trying to do with these other frequencies. Okay, first of all, I'll start off remote sensing. Again, very basic talk. I don't know what everyone's background is, but on the surface of the Earth, we have this atmosphere between us and space, and one of the features of our atmosphere is it is pretty opaque to electromagnetic radiation, except for two windows. And for years, I had a talk that actually came from an astronomy lecture in which everything was reversed because it was frequency and not wavelength. So I might say things in reverse in this one, but I got this much nicer image from a NASA website. The two windows are okay, so this is in terms of wavelength. The two windows are the radio window, if you're familiar with radio astronomy, Earth's atmosphere is pretty much transparent to about 3 decades of frequencies, from about a few, maybe 100 megahertz up to, tens of gigahertz, maybe almost going to, 40, 50 gigahertz around there. Pretty transparent. There's some effect of the atmosphere, which can be useful for remote sensing, but that's a very useful window to use. Okay, then it starts getting opaque again, and then we get to this optical window where things are very complicated. So the response of the Earth's atmosphere in optical frequencies depends very strongly on the weather. I mean, that is a common feature. You go outside, sometimes you can see the stars, sometimes you can't, right? And so this is, again, where all optical astronomy takes place. We also use it for remote sensing, going the other way, going from our instrument in space, looking down on the Earth. Okay, and then above that, pretty much is opaque. I think that is good because I think some of this stuff is not, may be harmful to us, so it's blocked out by the Earth's atmosphere. Okay, these two windows, only two ways of sensing what's going on with the Earth. I'm going to be talking about this one, the radio window or the microwave window. Okay, so I said, microwaves are very useful because there's much less of an effect of the atmosphere. So there's traditionally, classical microwave remote sensing takes one of two approaches. It's either passive, and in which case we sense, the brightness temperature of the Earth's surface, or, at certain frequencies, there is some effect of the atmosphere. So we look at the brightness temperature of the atmosphere, of the ocean, of vegetation, whatever. And then I can relate that to, an ideal black body on the surface, and that's going to be some properties of the physical temperature of the surface. And the relationship between those two is this emissivity. And emissivity depends on dielectric constant, and dielectric constant of natural media depends on a lot of different properties of that media. If I pick different frequencies, that sensitivity is different. I picked a classical application of passive radiometry, that is soil moisture, where here I have the moisture volumetric, volume of water over volume of soil, various ways of measuring that, and the dielectric constant, real and imaginary parts. So we get this idea that, as the amount of water increases, it's got much different dielectric constant in the soil. So by measuring this emissivity, I can extract the soil moisture content. This is what SMAP does, this is what SPOS does. There's some other older instruments that do this classical application. Okay, active remote sensing, or it's a form of radar. I'm transmitting a radar waveform. I'm looking at the backscatter. It's applied to remote sensing. It's sometimes called scatterometry. Classical scatterometry application is ocean winds, where here I show the scattering cross section, which kind of plays a similar role as emissivity, in that that's the one term that connects the geophysical properties to the electromagnetic properties. Okay, so scattering cross section shows up in my radar equation. It's a non-dimensional quantity. I multiply it by the resolution cell area. I get something that is a equivalent size of a perfect reflector. So in radar applied to things like air traffic control, this will be the apparent size of the aircraft, to radar, which could account for, the structure of that body. Okay, so if I look at scattering from the ocean surface, I will see that scattering is very dependent on the direction of the wind. So this is a relative azimuth of the waves to the view angle of my radar, and the direction of waves is sensitive to the wind. So the spectrum of waves in the direction of the wind and the spectrum of the waves perpendicular to the wind is different. So I get a different measure of the scattering. So I can look at this kind of sinusoidal effect. I can see that, 180 degrees is not exactly the same as 0. So there is a upwind, downwind anisotropy, but it's very weak. Okay, there's a whole books written on how to process the data, but this is an example of active microwave remote sensing that's really one of the classical ones. Okay, signals opportunity kind of merges these two, and I'm going to use the term third way of microwave remote sensing. So signals opportunity says, okay, I have an existing transmitter, which could be, in the case of GNSS, a navigation satellite, could be a communication satellite. In principle, it could even be an astronomical source. There's been some work I've seen using the sun as a source of radiation, but whatever. The point is, it's non-cooperative. We are not controlling the signal that's being emitted. We maybe know some of the general statistical properties, but we don't need access to the signal. We don't need to know the data that's being transmitted or anything like that. And so it's being emitted for its own purposes. Some of that's going to users on the ground. Some of it is going to scatter from the Earth's surface. And a small amount is backscattered. So if I'm using the equations for active radar, this is what I'm going to be looking at for radar. A very small amount is backscattered. A much stronger signal is forward scattered. In all but the most, the roughest conditions, it's still near specular, so most of the power is scattered in the forward direction. And so I have my receiver, which is passive, that's going to look at this reflected signal and compare it to a direct signal. So in order to make this measurement, I generally need both the reflected ray path and a direct line of sight to the source, and look at comparing those two. We're looking at some things that maybe aren't going to need that exactly that way, but this is the general idea of what signals opportunity is. Okay, and I said it could become the third way of microwave remote sensing. The term reflectometry has also been used as well. Okay, so what are the observables we can get that characterize the surface? Possibly the intervening media, although I've seen very little in looking at the media that it propagates through. There's been some papers on ionosphere and stuff like that. But basically, the observables we can make be the reflectivity at the surface, some phase, if I have a coherent reflection, and on that note, just how coherent is it? Is it diffuse, is it specular, or somewhere in between? And kind of the general lowest level data product is work with something called the delay Doppler map, where you map the scatter signal in delay and in Doppler, because I have a moving receiver, moving transmitter, so we do get a spreading in Doppler. Okay, and then from this may not be a complete list of variables, but the common ones would be ocean vector wind or ocean winds. Getting directions a little more complicated. Altimetry, soil moisture, wetlands, sea ice, biomass, a bunch of things have been demonstrated. Okay, so this isn't a completely new idea. I have a very short history going way back to the early days of satellites, and this basically came out of some of the interplanetary missions or lunar missions in the late 60s, early 70s, and as kind of a byproduct of the communication link. So Tyler and Simpson, I believe, were at Stanford, who did a lot of the early work on this. They have these communication links for these lunar probes, and by looking at a model of the signal reflecting through a layer of the lunar regolith and reflecting on a different layer, your Fresnel coefficients, they could look at the characterization of the lunar regolith and basically put that in terms. One thing to put in terms of this is how rough that surface is, how deep it is, and that was helpful in planning the lunar exploration missions at that time. Okay, so later there was some demonstrations on Earth measurements going from communication satellite to an aircraft. In this case, I believe they actually transmitted their signal that they wanted to use, but reused a communication satellite. Could show the Doppler spreading. They characterize everything in terms of Doppler spreading. Then, how did GNSS get into all of this? Well, to talk about I call it the prehistory of SoOp. I think I still call this one so the prehistory of SoOp related to GNSS. I'll get in a minute why I call this prehistory, not history. The earliest paper talking about this that everyone now cites is from 1988, Hall and Cordley. And the bottom line, their conclusion is they looked at, can we use the GPS constellation, which was still at that time predominantly a defense system. It may have been first, I don't know exactly when it opened up for civilian use. I think it was the late 80s. It didn't really become widely available to the mid 90s for everyday civilian use. But so they did a study. This is a conference paper from IGARS. And bottom line, incapable of giving useful performance. Okay. So 1988 decided this is not worthwhile to pursue. The problem is they were looking at this as backscatter, not forward scatter. Okay. So the numbers are much worse than backscatter, but much less of the signal is scattered on. Okay. So fast forward, I'm finishing my PhD, not in remote sensing and navigation. And I came across this paper from Institute of Navigation. So this is more an engineering navigation conference, right? We'll get into how to improve navigation, design receivers, stuff like that. And they were reporting this experiment and kind of a concern of flying over oceans, the possibility of capturing the reflected signal and for the receiver getting confused with that reflected signal and trying to do a navigation with that reflected signal. So, if I now have an additional path delay of this reflected signal going to this receiver on this aircraft, and if the receiver locks onto that and it goes through the navigation solution equations, it's going to get a really bad solution to navigation. Okay, so even though this is, just a conference paper, very engineering focused, they actually did extensive analysis of how the scattering on the ocean surface works and how it changes the structure of that signal. And I had not seen any of this kind of stuff before, so I started going further into that. And then that led to the idea of proposing to actually use these GNSS signals, beneficially as a remote sensing tool. So this is now I call the history. But basically, what I'm saying is history is after we kind of took a certain approach, not this backscatter or anything like that, but we kind of came up with the general approach to signals opportunities that's pretty much still used today. And so I was still finishing my PhD. This was from 1996, I think. So I graduated a year later. This was a project I was working at NASA at the time. I got internal funding to do this. We built this receiver. I'll show a picture of the receiver on the next page, and collected some data over the ocean. This empirically showed that this cross correlation between the codes in the navigation signal, which is the key to how navigation works, and the reflected signal gives a measurement of the roughness of the surface. So we published this internally, and then we wrote a GRL paper on it in '98. At the time, we were unaware. Manuel Mondier at STEC had written this other paper in the ESA journal, in which he proposed using this as an altimeter. So basically, he's looking at an altimeter waveform. We're trying to find the, some point representing the path delay, where what we're measuring is this change in the shape between, high significant wave height is how he characterizes it, and calm. Okay, so that sometime after we published this paper, we became aware of this other report. Okay, so this is the receiver we built. That's what I looked like in 1998. 1996-ish. Okay, that is Steve Katzberg, my co-author. We built this receiver based upon basically a development kit for GNSS receivers, because that was becoming a new thing at the time. And configured to find an aircraft. This is our first scatter plot where we flew along the TOPEX altimeter ground track and did a kind of empirically based wind speed retrieval. Okay. So I'm going to say a little bit about how GNSS reflectometry works, and then we're going to get to how this can be applied to other signals, and maybe a little discussion of why do we look at GNSS first. Okay. Navigation signals are designed for measuring position. So the core, and to make this an hour long, I cut out my tutorial on how GNSS works, but the basic idea is you want to measure a time delay. Time delay from your satellite multiplied by speed of light gives a range. So you imagine solving for your position. I have all of these strings between my receiver and my transmitting satellite, and I'm going to move to the point in which I tension all those strings and I solve for my solution. Okay, complications, of course, the signal doesn't always propagate at the speed of light, so I got to correct for the ionosphere. My receiver has a different clock than the constellation, so I need to add another satellite to solve for that. But the key thing we need to understand is the signals are designed for measuring a delay. And they measure the delay because they use a known structure in the signal called pseudo-random noise. It has, as best as we can, the properties of a long random sequence, even though it's entirely deterministic. It's generated by a very simple algorithm. It's kind of a relative of the random number generators that many of you use in your computational work. Okay, but by measuring the cross correlation between that received signal and an identical copy of that code, we can align those two codes relative to the local clock and estimate the time delay. That's the key to how navigation works. So what happens if I have a receiver and I have and to simplify this, let's assume we have an infinitely flat surface and my transmitter is out at infinity, so all my incident rays are parallel. This is a good approximation from an aircraft or a tower or something like that. Now I have my receiver up here. Okay, so I have these rays far away, parallel to the surface. One of those, shown in green, is going to get to my receiver. Okay. One way of thinking about this is I can also represent this as the same problem as if I move my receiver, to its reflection below the surface, then I just have basically a single path delay to my receiver. The signal is going to look no different than it does to in navigation. I'm going to get a nice cross correlation with a really clear peak. My navigation receiver is going to try to track that peak, estimate the delay to that peak, and that's how I get my measurement. Okay. And of course, if I'm using this for navigation, I'm going to get a really incorrect solution because I believe I'm below the surface. Okay. But things get interesting as the surface gets rougher. So now we have a rough surface, and depending on how my facet's oriented, I may have multiple ray paths that reach the receiver. Okay. Now the surface is all random, so from one instant to the next, the exact combination of those ray paths change. So my output now, my cross correlation is going to be a random process. But if I average that, I get some shape that I can fit to a model. But the important thing is now I notice my trailing edge is going to start to spread out. I'm having more delays that are longer than that specular point delay than shorter. So it's going to spread out in the long dimension. And then, of course, as my surface gets rougher, I have more delays reaching the receiver. And again, my trailing edge is going to spread out more. And my power at my peak is going to decrease because the amount of power from that specular reflection is going to decrease to put it to the long delays. Okay? So this area that's apparently illuminated, sometimes called the glistening zone, from the that covers kind of the area that's illuminated that reaches the receiver. Okay. So I showed some examples of this. This is a classical picture from the first GNSSR conference, which was just held down, about east of here, 22 years ago. Wow. In which we show sun setting, and we can see kind of this rough ocean surface. We don't see an image of the sun, but we see kind of the area covered by that incident power, right? So we see some area that's covered. We see kind of a decreasing, and then we see, outside that range, we don't see a reflection because the orientation of the facets are not such that I can reflect power back to my eyes. And then here where the surface is less rough, it's a smaller illuminated area. Okay. In the case of a specular reflection, I actually can see close to a mirror image of the sun. So this is an example. It's very flat surface. Okay. I'll go through a little bit about how this actually maps from points on the surface to the receiver. I don't want to spend a whole lot of time on this, but the important thing I'll bring up is that I didn't talk about Doppler. Transmitter and receiver are moving, so not only do we get a range of delays, each one of those little facets will introduce some Doppler because the rate of change of that path delay is slightly different, right? So if I would plot do my cross correlation and plot my power versus delay, and then I vary Dopplers, I get this shape that generally takes the form of this U shape or horseshoe shape, which is called the delay Doppler map. So this one slice through 0 Doppler, that will be those plots I showed earlier. Okay, so if I look very carefully, and I map my points on the surface that correspond to equal delays, I see that they are approximated by ellipses. I think they're exactly an ellipse if I have the case, again, the perfectly flat surface towards that infinity. But it's a reasonable approximation in more realistic cases. And then my Doppler, isodoppler curves take the form of these hyperbola. All right, so if I pick a given point here, it's an intersection between one delay and one Doppler, and I look very carefully, I will see that, I think I said this incorrectly. These are the Doppler lines going this way. I'll talk about what AD means in a minute. Okay, so if I look at like this one example of a given delay, given Doppler, I see that I have an ambiguity. I have 2 points on the surface that fall within the same ISO range ellipse and the same ISO Doppler zone. That's called the delay Doppler ambiguity. There is this one path A to B that corresponds along this kind of peak of the shape of this horseshoe. That is the ambiguity-free line. Okay, so it's not so easy to invert this whole thing and get an image. Okay, so I've spent way too much time on that. The important thing is kind of get the idea of what the fundamental measurement is. Now, if a surface is coherent, all the power is going to be within a very small region of delayed Doppler space. So a typical example. And we adjusted these amplitudes to be the same. So you see the difference. And then for the rougher surface on the ocean, it's not coherent, it's diffuse, and we get this horseshoe shape. Okay. If I look at what I'm actually measuring, after I do my cross correlation and delay and Doppler, I have a random variable that's complex. But if I take the magnitude of that squared, I get something that's going to have units of power or energy, if I paid attention to my calibration. But still it's a random process because the surface is random. Even though there's no noise, I have no receiver noise in this. This is just due to the randomness of the surface, or sometimes called speckle. Okay, so I take the average of this. I get this model, which is basically a radar equation. So the parts that go quickly through this, delay Doppler map is a function of my delay in Doppler. So inside my receiver, I'm varying delay, varying Doppler, generating one realization of that. Okay, the surface depends on a normalized radar, normalized bistatic radar cross section. Again, non-dimensional quantity. That's kind of the ratio of an ideal reflector area to the actual area in the surface. And this is where the geophysics comes into play. This could depend upon the signal I choose, the polarization, the frequency. It can also vary across my surface from space. That glistening zone can reach to hundreds of kilometers, and the reflectivity at the surface. Everything else is basically a radar equation. I do this ambiguity function. This represents the effect of the delay in Doppler. So this is the effect of filtering with the finite integration time, and also the delay due to the shape of that the signal autocorrelation. And again, everything else is radar equation, 1 over r squared, transmitted power wavelength, effective area, all that stuff. Okay, integration of the collision surface. Okay, so some of the scattering cross section, I'm just going to show the form of 2 of them. Coherent, I have a delta function because I'm only going to get strong reflection along one path, right? So if I plug that in, I can get everything in terms of magnitude squared or Fresnel coefficient or reflectivity. Depends on polarization. If I have a rough surface, I get this classical result that the scattering cross section depends upon the probability density function of surface flows. And a lot of, you can derive this formally. It's a classical paper by Barrick in 1968. But the concept, I think, is pretty easy to understand. I imagine my surface being made a little faster. Okay, my normal to the surface is green. So that's green vectors are attached to the surface. That represents this Q vector here, right? So let me see, this represents a property of the surface. So this is what my PDF is representing, the random distribution of the green vectors. The purple vectors are the Q. That's the bistatic vectors. Notice the purple vectors are always the bisector of a given incident ray and the reflected ray. So if I have this case, I have an incident ray, reflected ray, and the Q vector is parallel to the green vector. That says I have a little mirror reflection on that facet, specular reflection. So basically, this is just saying average over the whole surface, the probability that I get something close to this. That's all it's saying. So how close I get those two being specular, the higher the reflectivity. Okay, so I'm just giving out about 15 years of research to when this turned into a mission, which was Cygnus, or 2 technology demonstration missions before this. But Cygnus was funded as kind of like a science demonstration mission from the University of Michigan. I was in the science team. This was some animation they did, and they have an algorithm for retrieving ocean surface winds. This is from 2018. This has been improved quite a bit, but basically, yeah, we are looking at wind retrieval in the tropics. Okay, so now I want to get to signals of opportunity. So I'll kind of summarize why GNSS. Why did we begin this with navigation signals? And the main reason technically is that they're range coded. They have this pseudo-random noise on them that allows us to measure the delay, and inherently then that allows us to map the reflected signal in delay and Doppler. As a key function of navigation, we use it for remote sensing. We can look at multiple satellites with the same instrument, the same receiver, because they all transmit on the same frequency. We can isolate them by their code. Communications person might call this CDMA, code division multiple access. Okay, again, known PRN code. That's kind of how this all works. They are in a protected spectrum. It's not protected for science. It's protected for navigation, safety of life, all of those things. So it is protected. L-band it's good sensitivity, soil moisture, salinity, maybe not the best, even for those, I'll get to that later. And for ocean winds, it doesn't, if the wavelength is larger than some of the fine structure on the ocean surface. So the physical principle that I showed about the distribution of surface facets, that is not how a scatterometer works. Scatterometer looks at higher frequencies and it looks at a Bragg resonance at one specific frequency in the wave spectrum. Okay, so maybe not the best for ocean winds, but it has some advantage. I should also say it does penetrate through the Earth, through rain pretty well, better in these higher frequency, which was the selling case of Cygnus. And lastly, I began my career at GNSS, so I got into this not from doing remote sensing as for my PhD, but I got into this from navigation. Okay, so about 15 years ago, some colleagues of mine and some of my students started brainstorming about what else we could do. What could we use other signals? Okay, and one thing that motivated us is, well, at the time, a lot of communication signals were in geostationary orbit. That's kind of changing. The market's now going to these large low Earth orbiting constellations. But one of the advantages of being in geostationary orbit is you have a fixed geometry. Okay, it's a little difficult to see at the poles, but you have a fixed geometry. They also cover a wide range of bands. I give an analogy to my real estate analogy. The spectrum licenses are kind of like the deeds to your property, and it's being able to transmit signals back and forth between space and the Earth is a very valuable service. So there's a lot of competition. So any place you're allowed to build something, somebody's going to build something there, right? So any spectrum that's available, somebody's going to be transmitting something on it. Okay, cover the full range of those 3 decades of frequencies that penetrate through the Earth's atmosphere. The problem is those signals are designed for data transmission, not ranging. They don't have this known code. They're actually, their purpose is transmitting new data. Okay, so our hypothesis was generally that, well, okay, if they know what they're doing, so they're going to have the maximum use of that spectrum. They're going to compress the signal as best as they can, use encryption. All those things are going to turn any communication signal into noise. So we said, okay, we can approximate this thing as a band-limited noise, random, and as long as we have the direct signal, we don't really care what each bit is in the communication signal, as long as we can assume it to be random and we know what the shape of the spectrum looks like. Okay, so this shows the spectrum allocations for communications. We see there's stuff in yellow all over these 3 decades of frequencies. Okay, so we had this idea, and so we did some brainstorming. And okay, well, what's a thing we can do that we can't measure in any other, that we can't measure with other instruments, other microwave frequencies, but we could do with SoOp. And so the idea at the time came down to, well, SMAT, SMOS, all these L-band soil moisture instruments have a limitation. The L-band penetrates the soil about 5 centimeters. Okay, but we really would like to know what the structure of the moisture profile is below the surface, right? Because that impacts how much water is getting into plant roots, how much water is going into storage and all of that. So we said, let's look at E-band. So I did some research. Okay, so this just shows penetration depth. GNSS is here. E-band is here. This is even lower. This is I-band or VHF. And so we get penetration depths of 20 to 30 centimeters, but with L-band, we're either, depending on the soil moisture, either below 5 centimeters, or with very dry soil, we can get up to maybe 15 centimeters. Okay, and they call it the so-called root zone because that's where plant roots, those right here, average go down about 1 meter. That's where they absorb water. So closing the hydrological cycle is important to know that. Okay, so why aren't there P-band microwave instruments in either active or passive? Well, there's several technical reasons. One is, for my passive measurement, my size of my resolution cell in the ground is going to be proportional to the diameter of the instrument, and inverse proportional to the diameter of the instrument and proportional to the wavelength. So for a given resolution requirement, I have to keep this ratio wavelength to instrument diameter, aperture size the same. Okay, so if I go to P-band, if I go from L-band at 1500 megahertz down to P-band at 300 megahertz, I now have 5 times the size of my aperture to keep the same resolution requirement. Okay, and that had been studied. This was a concept study from probably like the early 2000s called MOSE. And they came up with the conclusion you need a 30-meter diameter antenna. So this is, $1 billion mission probably to launch this thing. ESA, I think it's going to be launched this year. ESA Biomass is also on P-band for 35 megahertz. It's an active radar, but they still need this 12-meter antenna. And again, this is 10 years in development, probably upper hundreds of euros total cost, expensive missions. Okay, the second thing is that these bands are heavily used for other purposes. So ESA Biomass is limited to coverage in the red and yellow areas, prohibited from coverage in North America and Europe because those bands are used for space tracking radar in those areas. Okay, and then lastly, because they're heavily utilized, there's a lot of radio frequency interference. This actually comes from a radio astronomy site, but it shows exactly what I wanted to show. This shows the spectrum, 225 to 480 megahertz, range of what we consider P-band or I-band. And notice this, there's really highly powerful signals here and here. It turns out these are from geostationary communication satellites. So ideas, can we use these that are already occupying the band? There's some weird set of units here, but pretty high signal noise ratio above the noise floor, right? Okay, so around 2003 or so, I wrote this proposal with NASA to develop an instrument demonstrator, and it goes on, on this NASA aircraft. P-band antennas, we use a pair of them and do some very crude beamforming. The satellite's a geostationary orbit, so we fly east to west. We only can make measurements in one direction because the antenna's only on one side of the aircraft over this instrumented area in the in Oklahoma. These are all soil moisture sites in this agricultural research site. Okay, so this is kind of like a prototype instrument development grant looking forward to a satellite mission. These are some of the results we got, and unfortunately, I've only published a very small amount of this because we basically did this, wrote the proposal for Snoopy. I have a ton of data. I finally got some funding to actually go back and really process this from a scientific standpoint and really understand what we're measuring. But we showed the fundamentals, and so here we show a lake, and we kind of look at what the color here indicates the strength of the reflectivity retrieval. This is approximately the size of the 1 Fresnel zone resolution. So we're detecting these water bodies. We're seeing some sensitivity to soil moisture, even though it didn't rain for all the days we were out there. We did see some possible RFI. And on the basis of that, as an engineering demonstration, we got funding for Snoopy, which was a technology demonstration from a space mission. I'm watching the time. I'm a little bit behind schedule. I'll go to kind of just summarize Snoopy. Well, again, it was a technology demonstration, not a science mission. And this just shows it's a 2x3U CubeSat. The antennas were these little cross dipoles. We used autocorrelation, so we're receiving direct and reflected signal interfering in space and extracting reflectivity from that autocorrelation. We developed some operational tools. Purdue was a science operations center. NASA Goddard did the mission operations. These are some of the tools we developed to plan data collections. We do have a receiver that we built that's basically a radiometer, a radio telescope. This is on one of the agricultural fields at Purdue, and we're looking at to kind of give measurements of the variation signal power and the shape of the spectrum, which we do know theoretically, but we wanted to validate that since we're using a non-cooperative source. Okay, this just shows some simulations we did. The first data. Okay, I should also mention while Snoopy was being finally prepared for launch, we had another opportunity. Spire is a private company. And they have this constellation of satellites, and for communications and reconnaissance and stuff like that. We actually don't know what the main purpose of the satellite was, but they have a software-defined radio that operates within this band with the dipole antenna. And this one satellite had reached the end of its mission, and they said, "Well, we got a few weeks left. Do you want us to collect some data for you?" So we got some funding for them. We collected data, collected a minute of data. We were able to downlink about 9.5 seconds before the satellite re-entered. But for what we got, we can clearly show the feasibility of using this autocorrelation with a single antenna to see the direct and the reflected signal. So here we see the autocorrelation at 0. This is the direct. here we see the autocorrelation at the specular point that we predicted from the orbit model. And you can see kind of it changing a little bit. So we have high signal noise ratio for this little gap. Okay, and then in a minute, we might have some RFI. Somebody's going to get this flat there. I think so that we see this like thing that's filling up the power there again. So those may be RFI. We don't know. But the important thing is that we got this coherent signal. We went in with a lot of uncertainty in the orbit. We fit it to a map on the ground. This is in the middle of winter, so it's all frozen ground. And we see that, well, if we plot the specular point over this region, we see this increase where we're crossing over this lake. It's a frozen lake, but we had a model for a frozen, frozen water, ice over water, reflection coefficient. We don't know the attitude at the time, so we took a range of antenna gains. No realistic. Okay. SoOp, this shows our integration and test with SoOp. This shows our deployment from the space station. It was launched just a little less than a year ago, deployed from space station a month later. It was carried along with another satellite, so both of them were deployed at the same time. I think this is SoOp. Okay, so we launched SoOp. We had some problems with SoOp. Eventually, the attitude control system failed. That was part of the satellite bus. The instrument worked fine, but we're able to collect a few data captures. I've been processing this one off the coast of Brazil, where we show we do get a coherent reflection. So this is the autocorrelation at around 0 around the direct signal, and this is the autocorrelation of the reflected signal. The specific data channel band we're using has a number of independent channels. So we show we got that. More recently, I don't have the results here. We believe we've seen reflections from 2 satellites. So we actually have 2 specular points. Okay. So I'm quickly running out of time. I mean, I want to say about what I'm doing with P-band. I'm recently funding. Well, I have an award letter. I haven't actually gotten the funding, so I don't know what's going to happen with that, but that's a separate issue. I have an award letter to continue this research, looking at developing algorithms. And we have a tower-based instrument. I'll maybe skip through some of this. These are some trade studies we did, a combination of different frequencies. This is our tower-based instrument. This tower is a portable cell tower. I can raise it up to 30 meters. And we have the possibility of doing 4 frequencies, except for the lower frequency, we really only can put one of these on at the time, either the 137 or the 360 megahertz, because of the weight and the moment on the tower. We start breaking things in the tower if it have too much of a wind load on it. Doing these measurements at this agricultural field at Purdue. This shows our projection of specular points. We've installed soil moisture probes at these locations. I have internal money from Purdue to continue this this year at a research forest that's very well calibrated with the School of Forestry. They've gone out and mapped the plots with different tree species and serial numbers in every tree that's there. So it's very well managed for ground truth. And so we're going to look at that as developing algorithms. Specifically in the case of the forest, we're looking at fire risk prediction. Okay. Got like 5 more minutes. I know my limit here. Okay, so I'll say another thing going to the completely other end of the spectrum, and that's look at wideband signals at KU and KA band. Okay, and we did some early work on this. We've not gotten much interest in continuing it further, but I want to talk about the use of signal opportunities for altimetry, and this shows why that may be important. So here we have a 9-day simulation. This is off the coast of California. I think this is Monterey Bay. I'm not absolutely sure. And so we have this some ocean model here, and then we simulate the SWAT altimeter. And over this 9 days, so SWAT is like, I think, a 21-day repeat mission. So I've showed this is the best coverage SWAT gives. So over 21 days, and maybe many days, it doesn't have any coverage at all. Okay, so now I combined this with, or actually, for comparison, I looked at using an 8 satellite constellation, looking at geostationary signals of opportunity. And we see we can fill in a lot more samples between these SWAT overpasses. Okay, but in order to do altimetry, and I know people want to do GNSS-R altimetry for so long, there's a fundamental problem. The altimetry precision depends most strongly on the bandwidth. So this all goes back to the same problem with navigation, right? If I have a wider bandwidth, the correlation time goes inversely proportional to bandwidth. that shape of that triangle gets narrower with higher bandwidth. Okay, so in order to be the scientifically useful altimetry requirements of 2 centimeters, say, I need a bandwidth that's going up to a few hundred megahertz. All right, regardless of the signal strength. So I can use the biggest gain antennas I want, all the signal processing. I'm limited by that bandwidth. And the widest band GNSS signal that I know about is Galileo E5, which is 80 megahertz, I think, on both halves of it. But these communication satellites in geostationary orbit, and now these new low Earth orbit ones, have hundreds to a gigahertz of bandwidth. So we had this experiment. We got some funding, back in 2017 for this. This is a calibration site for that NASA's used for a long time. It is this oil drilling platform that I think is no longer being used for oil drilling. But NASA had an agreement. We put these, and these are basically just commercial direct-to-V antennas. We modified them, and we were able to demonstrate altimetry that met the theoretical limit. So here we have a measured height, and we compared it as LiDAR as a reference, and we have theoretical limit for this experiment of fused 4 centimeters, and we showed that we were indexed at this case in which we believe we are seeing the interference of 2 spot hidden in the same satellite. Okay, so conclusions. Signals opportunity, microwave remote sensing outside of the bands protected for science, right? We can use, the real estate someone else is paying for, right? We can use someone else's communication satellite. One of the applications is subsurface soil moisture. Low frequencies penetrate deeper into soil. SoOp will demonstrate, this was maybe before we actually have the data back. SoOp, has pretty much demonstrated most of the key feasibility with only a few amount of data. We have an experiment looking ahead these wideband communication sources. We can get hundreds of bandwidth for free to help with altimetry. Okay, and so my last conclusion is there's a lot of other things out there that are signals we can use. I just put some examples here. So there's a lot of new things that we can do using existing signals. Okay, and some list of my funding that was supported here. Okay, thank you very much.
Thank you, Jim. Thank you very much. Also, to keep pretty well on time.
Okay. 5 minutes over.
Are there any questions for Jim in the audience? No? Let me check the chat.
Okay.
I don't see any questions on the chat either. No? I might have a couple of questions. Given the audience, and given that many of these techniques that we use were created or inspired by techniques used for planetary sciences and exploration. Do you think so? Is there anything that we do that could go back to a space again?
Right. Yeah, I mean, there's some, and actually, I didn't include any of that in this. We're still kind of very formative stage and a few ideas, but some of the things to consider is, okay, this bistatic measurement geometry, it does have a different response to things on the surface, right? So there, I'm working with some planetary geologists at Purdue, looking at, well, can we measure some things that conventional radar isn't able to measure. So that's one thing. Also, there's a plan to, explore the moon with cislunar space. Their communications is a big part of that. So there's been a lot of work done in defining a communications architecture for some kind of longer term presence on the moon, right? So as much as possible, if we can overlay measurements of that communication infrastructure, we can save money from having to launch a separate instrument, get a separate spectrum allocation. I've never gotten a straight answer on how spectrum allocation is handled off of the Earth. I don't know whether it's just, as long as you don't jam somebody, you can use whichever frequency you want. I don't know. But certainly, I mean, there is still going to be a limited amount of bands that we can use in those applications. So we are certainly looking at some applications in that area, but still very informative, very much an informative stage.
And what do you think about the challenges of this opportunistic, especially when it's not GNSS, when
you have no knowledge of the signal structure when you don't know the precise orbits of the
Right.
transmitting satellites. You don't know the clock errors.
Right. Okay, I'll talk about clock first, but that's kind of the easiest one. As long as you got the direct signal, we really don't care about the clock and the source, right? So I often, another phrase I've used is this is basically VLBI, but with artificial sources. We don't really care what's being transmitted from a given satellite. They got the worst clock in the world. As long as we have the direct signal as a reference, everything depends on our reference between those two, which is our own clock. Orbits is a big concern, okay, because if I go back here and I'm talking about a few centimeters, okay, that's the altimetric error. And actually, this doesn't scale. We will get, for a variety of reasons, we'll get about the same performance from orbit as well, because we use a higher gain antenna, so it's and also, I think this is what we call like a single shot error, so we can average this for multiple times. So we can get a few centimeters range error, altimetric error, okay? But if I'm going to solve that altimetry problem, I need to ultimately know the source, right? Because somewhere in that equation, I need the source geometry. It turns out the sensitivity to a geostationary source is about 100 to 1,000 to 1. So in other words, I could have a meter error in my communication source location of my geostationary satellite, and it's going to translate to about a centimeter error in the altimetry. So I don't need super high accuracy orbit. Unfortunately, the only thing that's publicly available for most satellites is the two-line elements, which are like 10 kilometers there. Two-line elements, so basically so that you don't launch your satellite close enough to hit somebody else, right? Okay, so another project related to altimetry, which I didn't mention, is we are looking at orbit determination using signals opportunity. So if we have ground-based receivers, again, this is exactly the VLBI problem, and we have decent clocks, but we don't need, with today's technology, we don't need exceptionally expensive clocks. We can look at the correlation along baselines of receivers and determine the orbit of geostationary source. Because it's geostationary, the dynamics are much slower, so the OD problem on the dynamic side is a little bit smoother. So the orbits is a concern. The other thing, and working through, as Cygnus moved along, working through the details, all these calibration issues become important. But power and polarization of the source becomes important. That's why we probably will need a ground-based monitor system, which for Cygnus uses that as well. They use a ground-based instrument to monitor the gain patterns of the GNSS satellites and monitor their power. So all these things need to be calibrated outright. So you don't get anything for free.
Thank you. This question.
Thank you for this very clear talk and very interesting. I think it's really a colloquial talk. And when we describe the history of all of this research, I remember the talk by Estelle and her group. He had so many talks. Now, my only question is about the last point that you raised with Starlink. Yeah, naively, one would say that with thousands of satellites, this could improve a lot. But what is your opinion?
I actually have a PhD student working on that. Yeah, I'll say the pros and cons. So these low Earth orbit constellations, yeah, if you have 1,000 sources, you can get really dense covering of the Earth, right? You also would get, since they're on low Earth orbit, kind of the opposite of what I mentioned about GEO. GEO, you have the same incidence angle, right? So in one sense, okay, I'm one less thing I need to calibrate out, right? So it's kind of like using sun synchronous orbits in the optical regime. I'm mostly removing the variation due to the sunlight. Geostationary sources, I'm mostly removing the variation due to an incidence angle. They move a little bit. Okay. On the opposite side, what if I want to get samples over a full range of incidence angles and really map out that BRDF or BDRF, I never remember which way, is a bidirectional reflection coefficient, really map out how the reflectivity changes with incidence angle. Maybe there's something we can do there, right? So maybe we take advantage of the fact that I have this, this rapidly changing incidence angle from the source in low Earth orbit. I can see how, for a given area on the surface, how that changes. And I can look at the reflectivity as a function of incidence angle, and I can make it more information back. So those kind of the advantages. Okay, and the other advantages, those are very wideband signals. They are 400 megahertz, 500 megahertz. Okay. There's several disadvantages. One is these signals use spot beams. So the way I understand Starlink works, and yeah, I mean, Starlink is an order of magnitude more complicated than any of these signals we're looking at here. Okay, so my PhD students spent a lot of time reverse engineering what Starlink is doing. Okay, and there's other people who look interested in using Starlink for navigation who pioneered some of this stuff. Okay, so one thing Starlink does is in order to get their very high their very high data rate, they need high power on the ground. So they have like a 37 dB electronically steerable antennas. They focus a beam on one cell on the ground. So the service is allocated by these geographically defined cells on the ground. So as the satellite moves in its orbit, its beam is focusing on one point and it's adjusting its beam. Okay, you can have multiple satellites focusing on the same beam if there's a lot of users there. Okay, so they all have their own algorithm to optimally do this, which we don't really have any insight into. So we need to somehow understand all that. All right. Okay, the other thing is, since you have this very narrow beam, you can't see the direct signal easily unless we're really close to the ground. So I'll just say we are working on some ways around that. Maybe look at some patents and stuff. So I'll just say generally that's a challenge. So we're working on some ways around that. So yeah, pros and cons. Order of magnitude more complicated than any of these signals we look at so far.
Yes, related to the Starlink satellites, which is the orbit height they have? Because if we want to place a reflectometer in orbit, it should be flying below.
Yeah, I think they're like 500 kilometers to somewhere in that range, right? So yeah, okay, so yeah, so several points there, right? So we may be limited to airborne instruments. There's this new field, this VLEO, very low Earth orbit, for like basically it's in between satellites and balloons. We get like maybe 200 kilometers. So you include something of aerodynamics in the satellite design. So the orbit lifetime isn't vanishingly small, but it is shorter lifetime. So there's a VLEO regime, maybe something you look at. Yeah, so that's a challenge, right?
It's in SoOp failed on your version. Is it planned to launch again? Or
I think they're waiting to see the data we get back. We are planning some follow-on missions. But I think NASA wants to see the data. And so we got for these samples we did collect, we're pretty sure we're seeing what we expect to see, and we can show Matt it validates the models. I also have this other funding to develop the science retrievals. So I think the steps that need to go between SoOp and a science mission, thorough analysis of data we already have, a development of the science algorithms, and also really formulation of the science case. So fire risk is a very important topic right now. So that's one of the things we're pursuing. But really need to, if you've ever been on these missions, I mean, formulating the science case and then how the requirements flow down from your hypothesis or your application down to requirements on the measurement. That there's quite a bit of work that needs to be done on that. Unless if there's opportunity to refly the SoOp instrument again, yeah, we'll take it. But I think the people with the money want to see what we learned from the first time as much as we can.
I just want, it's not a question, it's just to help everybody to understand. You mentioned the MOS proposal to use P-band some time ago with a 30 meters antenna. There is a biomass that will be launched soon. This is a P-band also mission with 12 meters antenna. And maybe people did not appreciate the size of this.
Okay.
How big was
Okay,
it?
well, I mean, the picture, you know, I mean, I have a model for it. It's, if you're familiar with CubeSats, it's a 6U. It's two by 3. So each U is a 10 centimeter by 10 centimeter, 10 centimeters squared. So SoOp will be 10 by 20 by 30 centimeters. And the antennas are just little cross dipoles, you know, half a wavelength. I think so little sticks coming out of it are half a wavelength. So there may be 0.8 meters or so. So I can carry about this big. Okay.
So it makes a big difference.
And one of the follow-on concepts we're looking at, I'm actually going to talk with Adriano, is this pocket cube, which is smaller than a CubeSat. And they're really, well, they're really cheap, but when you actually get to actually putting it, it's not really that much cheaper. The other lesson we found about CubeSats is, yeah, CubeSats are fine if you want to have students do something to learn. It's really not the economic benefit that do like a real science mission or really do a rigorous technology validation soon starts to dissipate because you ultimately want to have the same quality control and everything that you would for a big mission. So it's kind of a balance between those things.
Kind of more, if for example, you know, effective band for science didn't exist, what would be the ideal, you know, target? Because if I remember the curve for just the penetration depth, it's kind of flattening out to you know, for longer, smaller frequencies. But you say it's more a matter of bandwidth or the
I mean, where bandwidth matters is in some cases on the resolution, but we're assuming at these low frequencies, everything's specular, which bandwidth will be then determined by the wavelength of the signal. So at lower frequencies will give lower resolution, right? So, you know, if you had the ideal, well, you can pick whichever frequency you want. I mean, someone could maybe do a trade study between, okay, the resolution versus penetration depth, you know, and see kind of where that optimal is. But for the P-band stuff, we are assuming in our models that it's specular. So in that case, the bandwidth doesn't matter. You know, we could do a carrier, but then the only place bandwidth kind of matters is being able to separate the direct and reflected, because we do the cross correlation. And if you get and you know, this is some of the stuff with the drone that's concerned. If you get too low of an altitude, then the you know, that triangle for the direct and the triangle for the reflected start to merge. We are, in my model, I'm assuming those are separated. So that's going to put maybe like a really lower limit on the bandwidth. They don't separate those. But the resolution set just by the first Fresnel zone, which is kind of a subtle point when I talk about the antenna. Those, you know, low gain antennas have a really huge beam width. So basically, I have this huge beam width, but I'm only seeing power from the small area in the ground. So I think in altimetry, we'll refer to that as pulse limited altimetry versus beam width limited altimetry. So we can do this pulse limited, just set our resolution by the Fresnel zone.
Very well. I don't think there are more questions. Not in the chat, so we can close it here. Thank you again.
Thank you.